In this lesson, we are going to talk about determinants. Recall that in our previous lecture, we defined the determinant of a 2 by 2 matrix to be this one. You have AD minus BC. And we have seen also that a 2 by 2 matrix is invertible if and only if its determinant is non-zero. What we want to do in this lecture is to define the determinant of any square matrix, and we will also see later on that the matrix is invertible if and only if its determinant is non-zero, meaning to say we can generalize this statement for any square matrix. Before we discuss determinants, we have to define a few terms. First, let's discuss the minor. If A is a square matrix, the minor Mij is defined to be the determinant of the matrix obtained by eliminating row I and column j of A. Hence, if you have this matrix and this is your row I and this is your column j, of course this entry over here is your Aij, and let's say that this matrix is size n by n. This is n rows and of course n columns. What you need to do is to remove the row I and remove column j. And therefore, what will happen there? This matrix that will result will be what size? This matrix will be n minus 1 by n minus 1 matrix. For example, we have this matrix. Let us compute M12. So for M12, we remove the first row and we remove the second column. So we remove first row, remove second column. We now have, this is the determinant of 3, 2, 4, 1. And therefore that is equal to 3 minus 4 times 2 is 8. So that is equal to negative 5. Next, let's compute M23. We remove the second row and the third column. Second row, third column. This is equal to the determinant of the resulting 2 by 2 matrix, which is 0, 2, 4, 0. So this determinant is equal to 0 minus 4 times 2, which is 8. So that is equal to negative 8. Another term that we have to discuss would be cofactors. The cofactor is just the minor multiplied by either plus or minus 1. How do we determine which one to use, whether it's plus 1 or minus 1? It will be determined by the position ij. To be more specific, Cij is equal to negative 1 raised to I plus j times your minor Mij. What this means is that if you have this matrix, you have an alternating pattern of plus and minuses. For example, here in the 1, 1 entry, 1 plus 1 is 2, so that's why you have positive 1 here. Here you have 1, 2, and 3. 1, 2 is odd. 1 plus 2 is odd, so therefore you have minus here, and so on and so forth. Let us compute the following. We want to find C12 and C23. We already computed M12 to be equal to negative 5 and M23 to be equal to negative 8. So it's just a matter of multiplying this either by 1 or negative 1. In C12, this is negative 1 times 1 plus 2. And then times negative 5. So this is equal now to 5. For C23, 23 is also odd. So that is just negative 1. However, let me just write it here. Times negative 8. So therefore, this thing is equal to 8. Now we are ready to define the determinant of a matrix. If A is a square matrix, n by n, then the number obtained by multiplying the entries in any row or column of A with the corresponding cofactors and adding the resulting products is called the determinant of A, and the sums themselves are cofactor expansions of A. What is this saying? Let us break down the definition. First, it's saying that you get any row or any column. Let's just say that I will choose row I. What are the entries in row I? Those are AI1, AI2, and so on up to AIM. What is this saying? You multiply the entries, these entries here, by the corresponding cofactors. In this case, we have AI1. You multiply it with its cofactor CI1. Your AI2, you multiply it with its cofactor CI2, and so on, up to AIN, multiply with its cofactor CIN. And then what do you do next? You add up the resulting products. You add all of this. And that is now the definition of your determinant of A. We call this sum the cofactor expansion along row I. Similarly, we can define the cofactor expansion along any column. If this is your column J, the entries here would be A1J, A2J, up to ANJ. Again, you multiply the entries with their corresponding cofactors. Then A2J, C2J, up to ANJ, CNJ, and then you add up all the sums. This will also be equal to the determinant of A. Now take note that the determinant will not depend on the row or column. Whatever cofactor expansion you choose to get the determinant of A, you will still get the same number. To summarize what I have said earlier, this is the determinant of A, the cofactor expansion along the ith row, and this is the cofactor expansion along the jth row. So therefore, when we compute the determinant, let me just summarize what I've said earlier. You can choose any row or any column of the matrix, and then multiply each entry of the chosen row or column by the corresponding cofactor and add up the results. For example, let's compute the determinant of A. Here we have a 3 by 3 matrix. Again, it doesn't matter which row or which column you choose. In this case, I will be using the cofactor expansion along the first row. Why is that? Because these rows over here already have 0 entries. If I choose row 1, I no longer have to compute for C11 because whatever that is, it will just be multiplied to 0 anyway, right? Same is true for the third row. I will no longer have to compute for C32 because it will be multiplied to 0 anyway. This is the cofactor expansion along row 1. The determinant of A would be equal to 2 times C12 plus 1 times C13. Let us compute for C12. First, what are we going to choose? Plus or minus 1? 1 plus 2 is 3, which is odd, so this gets multiplied by -1. And then multiply it by the determinant obtained by removing first row and second column. When I use this notation, this refers to the determinant of a matrix as well. It's like absolute value of a matrix. We have 3, 2, 4, 1. That is equal to -1 times 3 minus 8. We get +5. Let's compute for C13. For C13, 1 plus 3 is even, so therefore, it's just +1. No need for negative. This is the determinant of, remove first row and third column. We have 3, -1, 4, 0. This is equal to 0 minus negative 4, that is equal to 4. So therefore, the determinant of A is equal to 2 times your C12 is 5 plus 1 times 4. You get 14. Just to show you that you will get the same number regardless of which row or which column you will choose, let us compute the determinant using column 2. Using column 2, we have 2 times C12 plus negative 1 times, this is C22. We already computed C12 earlier to be equal to 5. Let us just compute for C22. First, what is the sign? Is it positive or negative? 2 plus 2 is 4, so that's just positive 1. So we will now get the determinant of the resulting matrix when we delete second row and second column. We have 0, 1, 4, 1. This is equal to 0 minus 4, which is equal to negative 4. So therefore, the determinant is equal to 2 times 5 plus negative 1 times negative 4. And we also obtain the same number, 14. Using the definition of the determinant, we can now get the determinant of a 3 by 3 matrix. Let us expand this using row 1. Using row 1, it's A11, C11, plus A12, C12, plus A13, C13. What is C11? This is positive 1 times the determinant of, remove first row, first column, A23, A32, A33. This is equal to A22, A33 minus A32, A23. Next, let's compute C12. C12, this is 1 plus 2 is 3, so we have a negative 1 here. Times the determinant of, remove A12, we have A21, A23, A31, A33. This is equal to negative of, I will write C13 here. 1 plus 3 is 4, so it's just the determinant of, remove this and this, A21, A22, A31, A32. So that's A21, A32 minus A31, A22. So therefore, the determinant of A would be given by, first, this one, A11 times C11 times this, so we have A22, A33 minus A11, A32, A23 plus, I'm now on my second term, A12 times C12. So this was already be positive. So we have A31, A23 minus A12, A21, A33. And lastly, A13 times this one. A13, A21, A32 minus A13, A31, A22. I will now group all the terms containing the pluses here. And all the terms containing minuses. This is now the determinant of A, but of course it will be very difficult to memorize that. What you need to do is to copy the first two columns. And then you draw diagonals going down. Look at this one. A11, A22, A33, that is this term. And then next, go down, you have A12, A31, A23, that is this term. And then A13, A21, A32, that is this term. Next, you draw arrows going up. This one, that's, where is that term? A31, A22, A13. That is this term. This one, that's A32, A23, A11. And lastly, this one is A12, A21, A33. So that's a way to get the determinant of a 3 by 3 matrix. If you're going down, you always have plus, but if you're going up, you're having minus. So it's almost the same as in your 2 by 2 matrix, because for your 2 by 2 matrix, you have A, B, C, D. Going down, it's positive. If it's going up, minus BC. But of course, this system only works for 2 by 2 and 3 by 3 matrix. This method does not work for matrices of size greater than or equal to 4. Let us use that method in determining the determinant of this matrix. We copy the first two columns, 0, 3, 4, 2, negative 1, 0, and then draw diagonals. So therefore, the determinant of A is equal to, this is 0, 2 times 2 times 4 is 16. This is 0 minus negative 4 minus 0 minus 6. So we get 20 minus 6. We also get 14. This is the number that we obtained earlier. Next, we now have a 4 by 4 matrix over here, and we want to compute the determinant. Of course, we have no formula for the determinant of a 4 by 4 matrix, so we have no other option but to really use the definition of the determinant using cofactor expansion. Which row or which column are you going to use in this case? Take note that we can use the first row because it has the most number of zeros, or you can also choose the last column because it has 3 zero entries in it. Let's just stick with row 1. Using row 1, it's just equal to 3 times C11. And what is C11? This is already positive. 1 plus 1 is 2, so that's just positive 1. You do not have to multiply it by negative 1 times the determinant of the resulting matrix obtained by removing this. We have 1, 2, 0, 6, 0, negative 1, 3, 1, 0. And then this is 3 by 3 matrix. So you can use the previous formula that we had earlier. Or you can use cofactor expansion. Again, it doesn't really matter. Now, in this case, I will just make use of the previous method. Zero, so we have 3 times 0. This is negative 6. This is 0 again, minus 0, minus negative 1. This is 0 again. So therefore, that's 3 times negative 6 plus 1 is -5, so we have -15. That is the determinant of A. Computing the determinant of an n by n matrix is quite tedious, right? Because using the cofactor expansion, if you have an n by n matrix, you would have to compute determinants of n minus 1 by n minus 1 matrix, and so on until you reach, let's say, 3 by 3, or if you want, just up to 2 by 2 matrices. And this would entail a lot of adding up, correct? However, for special matrices, such as the ones that we will discuss, the determinants of these special matrices will be very easy to compute. Let us first define what are these special matrices. The first one is an upper triangular matrix. It has all 0 entries below its main diagonal. And a lower triangular matrix is a matrix wherein you have all 0 entries above its main diagonal. This is how an upper triangular matrix looks like. These are your main diagonal entries. And all of the entries below your main diagonal are zeros. The only possibilities wherein you would have non-zero entries would be here. So that's why it's called upper triangular, because the non-zero entries would appear here. Similarly, this one would be your lower triangular. Your main diagonal entries are here. The entries above it are all 0. And your non-zero entries would appear here. So that's why it's called lower triangular matrix. A diagonal matrix is one in which all entries above and below the main diagonal are 0, and therefore the only possibilities wherein you would have non-zero entries would be in your main diagonal. So that is why it's called a diagonal matrix. We want to find the determinant of a triangular matrix. Let us just suppose that we have this 5 by 5 triangular matrix, and then you can see later on that you can generalize this for any n by n matrix. I will expand it using row 1. So if I use row 1, I would get that the determinant of this is equal to A11 times, remove this and remove this, times the determinant of this matrix. I will use green. Okay, so that's green. However, when I compute for the determinant of this one, of this green, it's equal to, for green, it's equal to A22 times the determinant of, remove that, have the determinant of this one, times red. And then for red, again, I will use the first row of this, so it's A33 times, remove this, I will end up with pink. And that is A44. This is just 2 by 2, so that's A44, A55, minus 0, correct? Let us plug that in. So here, square is A33, A44, A55. That is your green square. So this is A22, A33, A44, A55. So what is this? The determinant of A is just equal to the product of A11, A22, A33, A44, A55. It's just the product of its diagonal entries. So in general, for any matrix of size n by n, the determinant of A would be equal to the product of its main diagonal entries. And here is that theorem. For example, we have this A. Take note that this is an upper triangular matrix. Correct? All the entries below the main diagonal are 0. So therefore, the determinant of A is equal to the product of 5 times 0 times 2 times -1. So this determinant is equal to 0. We've seen in this lesson that if a matrix has a lot of zeros in it, the determinant would be easy to compute, just like with your triangular matrix. In our next lesson, we will turn a matrix containing not so many zeros in it into something wherein it will have lots of zeros in it so that the determinant would be easier to compute.